Okay, so here's where we were last time. We were talking about linear approximations. And remember, the notation gets a little clunky when you're talking about linear approximations, and so we have these shorthands that we use to save our fingers, the inconvenience of having to write it all out. So we wrote down this shorthand right here, and I made the observation that is the thing that does it. That's the thing that you put in the place where the derivative used to be in a single variable linear approximation, and it makes it all work, right? So in particular, this formula that you get by putting that there has these two key features, that it agrees with f in value at the point A, and it agrees with f in all of the partial derivatives of all of the output components with respect to all of the input components. Again, at the point A as well. And recall that this, again, is an exercise, suggested exercise. I think it'd be a good thing. Give yourself a 2x3 or 3x something, low dimensional case. But do please work one out so that you can see how the matrix really does the job that it's supposed to do there. Okay. And another plug and chug example here. And this is just really a lot like the previous example that we had done. This general form, here turns into this. Because in order to get that, all you have to do is take the appropriate partials to get the derivative matrix, plug in the point in question to get the evaluated derivative matrix. It just goes right there where it's supposed to. Yeah. And everything else is just kind of a matter of writing it down. Okay. All right. Is everybody okay with that? Any questions before we go on? Okay. All right. Okay, a couple of last observations before we move to the next thing. We have this formula for the derivative matrix, and the formula that I've written down for you is in terms of elements. So you know exactly which elements are computed with which partial derivatives. But there's a couple of patterns to notice. One pattern you're going to notice is that by columns, these are all of the partials of the various components of f with respect to, in this case, x1. But notice that if you think about it, that means that this column as a whole is the partial derivative of the whole vector valued f with respect to x1, because you'll just do those partial derivatives one component at a time. So one alternative way to think of columns of a derivative matrix is that they are literally partial derivatives of the vector valued function. Likewise, you're going to notice eventually that rows, now if you think about it, what is a row? It's all of the various partials of, well, in this case, f1. We already have a name for that, right? The vector that is all of the various partial derivatives of any real valued function is the gradient, right? So neat thing to observe, you can think of the derivative matrix as a matrix, which as you should, and you can think of it as being made up of various elements, and that's all good, right? But the columns and the rows also mean something kind of natural, as it turns out. Okay. The other observation I want to make is, again, it's kind of annoying. The what we call the linear approximation is itself not a linear function. That's unfortunate, right? It is something slightly different. It's called affine. Don't worry about it. But why do we use the term linear if it's not linear? And the big idea is that df is doing most of the heavy lifting. Right, if you look at the formula for the linear approximation, here it is. Right, this other term over here, it's just a constant. Right, so yeah. Technically, it's not linear, but if you look at the part that is most of the linear approximation, that is linear. Okay, all right. So those are just quick observations. Okay, so let's talk about tangent lines real quick. I hope you all recall from single variable calculus that if you look at the graph then there is this thing called a tangent line. I'm sure y'all remember tangent lines. This is another situation where language becomes important. In single variable calculus classes, they kind of tend to blur the distinction between the linear approximation and the tangent line. And the difference is that one is the graph of the other. So we have previously talked about the linear approximation. This is a function. This is a purely algebraic object, right? It's just a function. The tangent line is not a function. The tangent line is a curve. It's a geometric object. Right now, it's closely related in that it is the graph. Right? You can see right there, it's the graph because we're setting a new variable equal to the output values of the linear approximation function. So anyway, that's just what the tangent line is. It's the graph of the linear approximation, not the linear approximation itself. Okay, fussy distinction, I know, but these kinds of things matter. So along the same lines, no pun intended, the linear approximation of a function of two variables, also a function, also a purely algebraic thing. This is not a geometric object. This is an algebraic object. It's a function. And we can talk about its graph. What do you get when you set it equal to a new variable? And we ran out of letters, so we had to go over to z. Right? That now is the tangent plane. So it's totally analogous to a tangent line. No big deal in that sense. And really the main point that I want to make here is just, do be careful to distinguish a function from its graph and make sure to use the terms, correctly. So if somebody asks you for the equation of the tangent plane, and if you were to write down, let's see here, let me just clear this all off. Someone asks you for the equation of the tangent plane and you give them this, it's just not right. I mean, that's not a plane. This is a function, right? Importantly, a function, not a geometric object. And if someone asks you for the linear approximation, and if you give them this, that's not a function, right? So anyway, careful. All right. Okay. The next few pages here are, I feel like a necessity. I feel like we have to talk through some of this, but we're not going to get bogged down in this very much. Here's the fundamental problem. It turns out that there are some nasty, sophisticated, deep questions that go along with the question of what do you mean by a differentiable multivariable function. In single variable calculus, these questions kind of aren't really there. A function is differentiable if you can differentiate it. And those synonymous things, right, if they happen, then there is a good linear approximation, that linear approximation being exactly what you write down from the derivative that you just computed. So the idea of, this question is, do I have a good linear approximation? Well, is the function differentiable? Were you able to take a derivative? If so, cool, right? It's pretty straightforward. In the multivariable context, it's weirder than that. And I'm going to start off with an example that's admittedly weird, but it remains that this is a nasty problem. So we wrote down a formula for the linear approximation. It involved taking partial derivatives, plugging into a particular form. Let's apply that formula to this function right here. Again, strange looking function. The values are either 1 or 0 depending on blah, blah, blah. Here's a picture of this function, the graph, that is. The graph of this function has value 1 if you're above either the x or y axes, right? And the value of the function is 0 otherwise. So the value of the function over here, for example, in the first quadrant, off of the axes, right? All zeros over there. Likewise, all zeros kind of over here, if you will, right? And also the other two quadrants, which I don't want to make my picture get cluttered. Okay, so graph of f, that being this function. Now, let's ask, can I compute can I write down anyway the formula for the linear approximation that we did last time? Well, I just need to compute various partial derivatives, and if we are looking at this point a equals 0, the 0 vector, right? The value of the function at 0 is 1. No problem, right? Both of the coordinates are 0, so the value of the function is 1. Can I take a partial derivative? How does this function change as I move, for example, in the x direction? As I move in the x direction, no problem. The function doesn't change at all as I'm moving in the x direction. It's just constant 1. As I move from the origin in the x direction, the function's not changing. Ditto if I look at in the y direction. The function's not changing in the y direction either as I move from the origin. Yeah, everybody good? Okay. So with all of this together, with the value of the function at that point being 1 and the partial derivatives both being 0, I can write down my linear approximation, and my linear approximation is, let's see, I have not used my colors prudently here. There's my linear approximation. Value of the linear approximation is just flat 1. And I can draw that on this picture. It's like this, right? There's flat 1. Now, is this a good linear approximation? No, it's abysmal. Absolutely abysmal, right? Now I'm going to try to explain why this is a terrible linear approximation. I'm going to have to erase some of the shading that I have in here. So just try to remember the blue function that we were approximating I have with the blue shading. The green linear approximation is just this flat plane up here at 1. So now with that in mind, and again, cleaning up so I can see better, let's think about what happens as I move toward the origin at an angle. Like that. Moving toward the origin where I never actually quite get to, of course. Well, the value of the function, everywhere on this purple line, neither of the coordinates is 0. The value of the function itself is 0. What is the value of my linear approximation? As I move along this same line, it is 1. And that's terrible, right? I have a clear error here. The error doesn't even decrease. The error, the difference between my approximation and the actual value of the function, that error just remains 1 all the way down. So, terrible, terrible attempt at a linear approximation. So, before we go on and try to fix this, point out, I followed the formula. I looked at the value of the function at the base point. I looked at the partials in both directions. I wrote down the formula. I got garbage as a result. So, there is apparently going to be a problem. Apparently, having partial derivatives is not good enough to know that your linear approximation is actually a linear approximation. Right, so that's bad news. Okay, let's try to fix this. Here's one obvious fix. Look, the clear problem you would think is all this error in there. Maybe I should just require the error to approach 0. That didn't happen here. This is obviously some example that I want to eliminate. if I require that the error approach 0, that would absolve us of any liabilities for this being called a linear approximation because we're ruling it out. Okay. Not good enough. Let's look at this example here. Here is a function whose graph looks like that. Let's suppose by some means or another somebody came to us and said, hey, I think this is a pretty good linear approximation right here, right? 3x. And of course that looks more like this. And of course, intuition-wise, obviously this is a terrible linear approximation. This is ridiculous, silly. Yeah, true, but the error, the difference between the right value and the approximated value does go to 0. Right? So here's the problem. This requirement that, it require that the error approach 0, nowhere near good enough. It doesn't even eliminate this obviously nonsensical, ridiculous candidate for a linear approximation. So error going to 0, not good enough. Everybody see the problem? So here's the improvement, the better idea. We're going to look at something called relative error. Relative error says, let's look at the error. That's my numerator here. How far off are you in the output with your approximation? But then let's divide that by magnitude of x minus a, namely divide by how far away are you from the input. Right? So output error per unit, in some sense, distance in the input. So another thing to try. Let's look back at this example that we were just looking at. And again, here's the function. Here's the candidate approximation. I'll try to do better highlighting that. And the error goes to 0, etc. But if you look at relative error, right? The error is 2x, which does approach 0. But the relative error is not 0 and does not approach 0. So this is why differentiability is not defined in terms of error. It just doesn't do what it needs to do. We need to require that relative error also go to 0. Vanish is the common term. So this picture in mind. This is why error is not good enough. Relative error is what we need. Now I show you that not because I don't want to get bogged down in details. That's not the purpose of what we're doing here. I just want y'all to have a good approximate idea of where does this all come from and what's the motivation and roughly what does it mean? Yeah.
Is there a time when relative error would go to 0 and error would not go to 0?
No. No, that doesn't happen. That's right. Yeah, it's a good question. Yeah.
The first example we did,
Yep.
X equal to 0 and Y equal to 0, Z being 1, is that off the relative error test?
Nope, that fails at 2, which it should, because it too was a bad attempt at a linear approximation. Yeah, absolutely. In fact, that one, the relative error, not only does it not approach 0, the relative error approaches infinity, and so that one really fails. Yeah. Okay, so here's the definition of differentiability. This is in the book, but a function is differentiable if, and furthermore, this is the linear approximation if a certain thing happens, and the formula is that you need this great big scary looking expression here to approach 0. And when you see this expression by itself, you're like, wait, what? Where did that come from? What are we talking about here? And I want to point out all this is relative error. That's it. And you can see that in the development of this expression. Here's relative error. Don't forget that error, which I guess I did in red, error is actual value minus approximated value. And don't forget that the linear approximation, and real quick, I am going to move some parentheses around over here. If you look at what I've got going on over here, I'm going to put these together, and then because of distributing the minus sign, that turns this into a plus. Notice that this L that I have right here as part of error is just that thing over there. So literally, on this great big thing here, all it is relative error. So function's differentiable if relative error approaches 0. That's all there is to it. Now, bad news. Working with this definition, extremely inconvenient. Sufficiently inconvenient that we are not going to work with this definition. Right? I wanted, though, for y'all to see the definition and have some sense for why this is the definition. It's because this is what gets at this idea of that we were talking about above, of making a good linear approximation. Another piece of motivation that I think is healthy for y'all to know is why this is important. And this idea of differentiability is the sharp condition. It's the exact condition necessary to be able to write down various theorems that we're going to be doing throughout the class. There's a few big ones. But anyway, differentiability is ultimately the natural notion of what we mean by a function that you can, in ways that we're going to need to be able to do, take real derivatives of in a real sense. Okay. All right, now a terminology thing real quick. Notice that this numerator up here, you can kind of group things a little bit differently, and instead of thinking of it as actual value minus approximated value, another way to just kind of move the parentheses around is to talk about the actual change in the value of the function versus our approximated change in the value of the function. So actual versus approximated value of the function is one point of view. Actual versus approximated change in the function, the other point of view. And heads up that this term here, increment, describes the actual change, and this term here, differential, describes our linear approximation of the change. And the really useful terminology, we're going to be using that throughout the rest of the course. Okay, all right, that's all we need to do with differentiability. Oh, I'm sorry, one other thing. The good news, where things become easy. There's a related idea called continuously differentiable. This is not the same as differentiable. Differentiability is the condition on the previous page. Continuous differentiability is a more powerful idea, which you would think would make it a more sophisticated thing, which you would think would make it harder to work with. And the wonderful, wonderful news is that it's the exact opposite. It's actually super easy to deal with. Continuously differentiable just means that the partial derivatives exist and are continuous. That's it. It's super easy, right? So glance at your function. Can you take the partial derivatives? And if you can, are those partial derivatives always going to be continuous? Which, again, you just kind of look at the function, and it's just going to be perfectly clear in most cases whether it is or isn't continuous. And again, this is not going to be we're not going to worry about anomalous sort of weirdo nonsense in this class. So the reason this is useful is because it turns out continuous differentiability allows us to conclude differentiability. And in practice, this is how it's done, right? Day in and day out. If you need to know a function's differentiable, check to see if it's continuously differentiable. Super easy to do. You've got to check for partials. Got to make sure they're continuous. Boom. Instantly you know the function's differentiable. You don't have to deal with all that relative error, inconvenience. So, nice little theorem. Just check it's continuously differentiable, celebrate. So here's an example of that in action. Let's look at this function right here. It's a polynomial. Let's ask the question now, is that differentiable? Seemingly a hard question. You look at the definition of differentiable. We're going to have to deal with relative error, it would seem. Nope. Let's come at it from the point of view of continuous differentiability. The partials are really easy to find. They're clearly going to all be polynomials, right? So super easy. You don't even have to compute them. They're obviously all going to be polynomials. Totally fine. Next, we note all polynomials are continuous. Old news, right? Old fact from, well, technically this is a slightly different, updated fact, but I hope this is a believable claim that's morally equivalent to a fact from single variable calculus. And so altogether, we know the partial derivatives, we know they're all continuous, and partial derivatives being continuous is exactly what continuously differentiable means. So the blue and yellow observations together tell me that I've got a continuously differentiable function. And if it's continuously differentiable, then it's differentiable per this theorem. No discussion of relative error needed. Everybody happy? All right. Another fact that's useful, we're not going to prove this, and you don't need to worry about the proof, but also true, every differentiable function is continuous, which by itself, as written, doesn't help us decide if a function is differentiable or not. It's the arrow's kind of going the wrong way. Right? So what we do is we use something called the contrapositive. If P implies Q, then not Q implies not P. It's a really handy fact to know. So you can just look that up, but Google it, probably contrapositive. The contrapositive here says if you have a function that's not continuous, well, then I immediately know it's not differentiable. So the contrapositive turns this into a test that allows me to decide, at least in some cases, on the question of differentiability. So, for example, this original weirdo function we were looking at, this oddball right here. This function, pretty clearly not continuous, right? Look at the graph. It's got these jump discontinuities in it, specifically at the origin, of course. Big jump discontinuity right there at the origin. Clearly not continuous, and because of that, because it's not continuous, it follows that it is not differentiable. Does that make sense to everybody? Everybody good? Handy sometimes. Okay. All right. So, I'll make a couple of innocent observations here. Here is a formula that we've written down for linear approximations. This is the general case, right, where we have a multivariable, because there's n inputs, vector valued, because there's m outputs. This is our general multivariable vector valued linear approximation formula. And quick freebie to note, F and L agree at A. That's one of the motivations for writing down that formula in the first place, right? So I could rewrite F as L in that term anyway. And then I can take this and move it over to the other side of the equation, and lo and behold, I've got what's going to turn out to be a really important equation right here. if you look at it the right way. And the way we're going to look at it is like this, that this says how much we change the input to the function relates to our linear estimate of the output change of the function by way of that matrix. Right? So said differently, the DF matrix, that's the thing that turns input changes into output changes. And if you think back to the very first thing that I said about derivatives, the first page of the whatever section is that we're in right now, that's what a derivative fundamentally is. It's a relationship between input changes and output changes. So, bam. So this thing df, and now here I'm writing the everything as differentials. This turns input changes into output changes, right? So df is the thing that does that. And so df, if anything is going to get called the derivative, if you had to pick just one thing to call the derivative that turns input changes into output changes most broadly in all cases, that's it. It's a derivative matrix. Right, now, I'll remind you that we've seen various different things that we've called derivatives. We talked about partial derivatives. We talked about the gradient vector. The gradient vector plays a role kind of like derivatives do in some cases. And so the gradient is a kind of a derivative in a certain context, a certain point of view. And then we have this DF matrix that is a kind of a derivative. And we're going to see another kind of a derivative coming up not too long from now. We'll talk about that when we get there. But this is the one that turns input changes and output changes most broadly. Yes?
Can we interpret small df as the change in the output or as the change in the linear approximation of the output?
Yes, the latter. So df, whenever you talk about an output differential, that always means that you're talking about the change in the value of the linear approximation. The actual change in the value of the function is, well, that's what calculus isn't really immediate. The single variable, first order calculus isn't good at, because derivatives just kind of keep track of, assuming that everything is kind of continuing on as it had been. Linear estimates don't do that well. So output differentials are always linear estimates. Right. Okay, so this thing, again, a little bit of terminology. df, we've been calling it the derivative matrix for a while. I'm introducing here that we can call it just the derivative. Full stop. It's the thing that turns input changes to output changes. That's what a derivative is. So a little bit of a weird idea. Y'all are accustomed perhaps to thinking of the derivative as being a number, right? Or a formula, but if you think about it, a formula is just a way of computing a number, right? But this is a different, fundamentally different structure. A derivative in a multivariable vector valued setting is not a number. It's a matrix. All right, sometimes called the derivative transformation because it's a linear transformation. Sometimes written as JF instead of DF. This is a reference to the fact that this is sometimes called the Jacobian matrix, kind of historical reasons, and still in use, right? So heads up, be aware. Some people are going to call this the Jacobian matrix. I'm going to slip up here and there, and just because of the way I was mathematically brought up, I have been accustomed to calling it the Jacobian in the past as well. So, anyway, all right. So here's a picture of what we're talking about, right? If you have a point here in a domain whose image is here in the target, and keep in mind what functions do. Functions take input points and give you output points, right? What the derivative matrix does it turns input changes, right? How much you move away from some input point into output changes. How much we, per our linear estimate, how much the output moves as a result. So that's what the derivative matrix does. It turns input changes into output changes. Everybody happy? The short version of this is that a function turns points to points. The derivative matrix takes vectors to vectors. Okay. All right. Now, twist on this. You can just take the existing equation and just divide both sides by dt. I don't want to get formal about this, right? But just intuitively speaking, this is the, effectively we're just going to divide both sides by dt. And now look what my equation turns into. My equation has turned into a different point of view on the derivative. Now, the derivative, it would seem, is something that I can multiply by input velocities, right? dx dt is a velocity. And it turns it into an output velocity. So again, same derivative matrix. It's still kind of input change into output change. It's just now it's an input, you might say, rate of change into an output rate of change. But it's still, if you look at it the right way anyway, it's still turning an input vector into an output vector. It's just that now the input and output vectors represent velocities instead of displacements. So I think it's a nice fact. You can think of the derivative matrix as acting on either, take your pick, displacements or velocities. Suit yourself. To be totally honest, I actually kind of like this one better myself, because this has the limit built into it. And so this is not even an approximation. This is exact, right? A velocity, shoot, did I get this backward? Oh, gosh, look at me. I'm sorry. I got my colors backwards. Okay, so green is the input velocity. I'm sorry. And then blue is the output velocity. Okay. I like this point of view better because velocities are instantaneous, right? Instantaneous rates of change. And so there is the approximation aspect of things is you don't even have to worry about that here. So this is my personal favorite way to think about what the derivative matrix does. Quick observation. Dot product with the gradient kind of does the same thing that the derivative matrix does, right? You recall, if you look back at the formula for real valued multivariable linear approximations, it involved the gradient vector, in particular dot product with the gradient vector, which I should have in purple. Why do I have that in blue? That's silly. So dot product with the gradient. So you can view dot product with the gradient in the same way as the derivative matrix. It turns input differentials into output differentials, just like the derivative matrix. So in this case, and again I emphasize, this is only for real valued functions. It has to be real valued in order to even be able to talk about the gradient vector. Right? But in that case, when you're talking about a real valued function, you kind of have a choice. You can think of this process that turns input vectors into output vectors. You can think of that as multiplication by the DF matrix, or, if you prefer, you can think of it as dot product with the gradient vector. It's really the same arithmetic. Both these objects, if you write down the formulas for them, both of these are just made up of the various partial derivatives. It's just, if you assemble them vertically as a vector, you call it the gradient. If you assemble it horizontally as a derivative matrix, you call it the derivative matrix. Okay. Higher order partials. Section 2.4. There's a bunch of stuff in 2.4 I'm going to leave most of it for y'all to read on your own. It's pretty straightforward reading, I think. Give that a read. I am going to talk about a couple of little subtleties. One in particular. Here's our derivative matrix. We've already seen that that's linear. Of course it is. It's a matrix. I want to talk about a different thing, though. I want to talk about the act of differentiation itself. Not df, but d. D being the process that takes a function, differentiable, so that it makes sense, right? The process that takes a differentiable function and turns it into a derivative matrix. Right? This action of turning a function into a derivative matrix. This too is linear. Right? So the resulting matrix is linear, right? But the action of differentiation also linear. So here's the way to write that down. Notice this is just our standard definition of linearity. On the left side, I have a linear combination before I plug into D. On the right side, I have the same linear combination after I've plugged those functions into D. And we get the same thing either way. So that's just linearity of this different thing. Is everybody okay with this as a statement? I'm going to show you an example. Just a quick moment here. Okay. All right. Okay, so example. Let's see, I'm going to zoom out so we can get this all on. Here we go. Okay, so here's a couple of functions and their derivative matrices. Now, make sure you can write this down. Do keep in mind that you got to keep it straight. Which are the columns and which are the rows? Don't accidentally transpose your derivative matrix. That's a huge problem, right? So make sure to think that through carefully and get it in the right order. Then I can also take a linear combination of those two functions, and I can talk about its derivative matrix. Now, this is just a matter of kind of multiplying out a couple of functions and adding per this formula for a linear combination, and then just, again, computing the appropriate partials, assembling them in the right order, et cetera, et cetera. Okay. So, with all that having been... Oh, yeah, question.
Where are you getting the 5f plus 6g from?
I made it up.
Okay.
Yeah, so this is just an arbitrary linear combination.
Okay.
Yeah. So just keep in mind, linearity requires that this works for every value of a and b, right? And for every function f and every function g. So I just made up an example. Okay. Yeah, totally. Okay, so we have an f and a g. There's their linear combination. And on the one hand, I can take a linear combination of the derivative matrices, right? So the same linear combination of the individual derivative matrices, or I can look at the derivative matrix of the linear combination, which I'd already done. Right? And notice, very easy to confirm this arithmetic. That's just arithmetic. And the result then is that, as it should be, the linear combination of the derivatives is the derivative of the linear combination as required. Okay, so this is just an example, but this kind of thing always works for differential functions. Okay, yeah.
So when you say like h is equal to 5f plus 6g, how did you get to the next part? Because I'm trying to like...
Oh, yeah. So I took, for f, I took this formula, and for g, I took this formula, and now let's just do this one coordinate at a time. All right, let's look at first coordinates. What is 5 times the first coordinate of f? Well, that's going to be 5x. Now I need 6 times the first coordinate of g. That would be 18y. We're going to add those up, and I get 5x plus 18y. So it's just, yeah, it's just cranking. Yeah, no worries. Yeah, it's just cranking it out. Yeah. Okay. All right. Okay, so differentiation is linear. By the way, y'all actually saw versions of this in single variable calculus. They didn't say it with the term linear, of course, but you probably did see, like, let's see, how would they have said it? They probably would have said differentiation is additive or something. Like the derivative of f plus g is the derivative of f plus the derivative of g. You know, and basic. So this was referred to as basic properties of differentiation. This is just kind of, you know, now that y'all know linear algebra, right? We can talk about terms like linearity and vector space and stuff like that. This is just a kind of a convenient way of saying that. Okay. Real quick reference. There's a product rule, quotient rule. In some cases, you do have to be careful and make sure that you only apply these rules when they apply. So take a look at the details that are in the book and be on the lookout for how you can take convenient advantage of these kinds of shortcuts. Okay. All right, let's talk about higher order partials. This is something y'all did in single variable calculus, no big deal. If you have a sufficiently, let's not worry about regularity. Let's assume everything is as differentiable as we want it to be. If you have a function of x, you take the derivative, still a function of x. So you can take the derivative again, right? Same thing happens with a function of several variables. If you have a function of several variables, you can take a partial derivative. The result, still a function of those same several variables. You can see that in action right here. Here's an example of a function of x and y. And I could take various partials. And the results, also functions of x and y, just like f was. And so because I can talk about the partials of this function of x and y, well, I could likewise talk about the partials of these partials. They're also functions of x and y. Okay, now when you do that, let's just look at the left side here. I take the partial of f with respect to x. I can talk about its x partial or its y partial. And it's just a matter of kind of writing it down. I mean, y'all know the rules for how to take partial derivatives of functions like this. It's really easy to do. Let's talk about notation a little bit. The notation's a little bit weird. Let's see here. Yeah. Keeping in mind that we started by taking the x partial, and now what am I going to do to the x? What am I going to do to the x partial? Well, I'm going to take a y partial of that x partial. So we did the x partial first, we do the y partial after, and notice the way the notation is written, these partials they get added on sort of to the left, because that's its notation. It's just how we write it, right? And, okay, fine. On the other hand, I could view it as, in sort of the Newtonian notation down here, x partial with an x subscript. And then how would I indicate the y partial of that? Well, by making a subscript to the subscripted thing. Right? So these are, I think, both pretty natural choices of notations for second derivatives, given our existing notation for single derivatives. And y'all have probably noticed the concern here. The concern is that when you use the Leibniz notation versus when you use the Newton notation, the green and the blue are in the opposite, right? It's super annoying. And so even though y is on the left, x is on the right, but here x is on the left and y is on the right, both of these refer to the same thing. And it is confusing And I'm sorry. This is just an unavoidable consequence of the existing notation for partial derivatives. So heads up, be on the lookout for that. Just keep in mind that you should interpret these accordingly. Now, one thing you're going to notice is that these two things are the same. And at first glance, you might think, wow, what a weird coincidence. The x partial of the y partial of the x partial, they happen to be exactly the same. What are the odds? Right? And then you think to yourself, well, wait a minute, this is actually kind of as it should be, because the rules for how we take partial derivatives, in some sense, only one factor at a time is really doing anything. And so you might be able to persuade yourself, for polynomials, for example, it's fairly believable, I think, that this is always going to work out. This is kind of nice. But it does not always work out. There are cases where it doesn't. There is a condition that has to be checked if you want this to work. The condition, to get the conclusion that we want, where we always get the same value no matter how you rearrange the partials. And by the way, don't get lost in the notation down here. This is just notation to represent that I'm going to do my partials in a different order on the right versus the left. It's just talking about rearranging partials. The condition is that the function in question has to be what we call CK. However many partial derivatives you're doing down here, that's what the K needs to be. So what does it mean for a function to be CK? K is a reference to how many of those partial derivatives you need to make a reference to, and the C is a reference to the fact that I need that many partial derivatives to be continuous. That's all it is. And good news, most of the functions that we're going to deal with in this class, most of the functions that you're going to use, I would think, anyway, outside of this class, in engineering classes or what have you, are C infinity, meaning that all of the partials, no matter how many partials you take, always continuous, right? So this phenomenon of rearrangements giving you the same value works most of the time, which is a really nice fact. Okay, let's see here. I've got 2.5 minutes. Okay, I want to do one quick thing here. I want to talk about what this looks like geometrically. We're going to do kind of the easy version, then we're not going to have time for the harder version here. I want to look at FYY. So the y partial of the y partial. If you think about it, the very first thing that we do when we write down FYY is we say, okay, well, I'm going to have to treat x as a constant. So I'm going to come down here into my picture. Notice this is a graph, by the way. We're going to restrict our attention to this cross-section in the y direction, right? And notice for both of these partial derivatives, both of them are with respect to y. So I could think of this as a y partial of a y partial, but I can also think of it as, look, I'm going to take f, I'm just going to look at this one cross-section in this one plane, and then I'm going to take literally the second derivative of that single variable function of y, because they're both partials with respect to y. And so the interpretation you get is exactly what you would think, this cross-section being a curve kind of like that. If the second partial is positive, then you would expect it to be concave up, like I have in this picture here. So this is a picture of FYY being positive. That's just concavity, exactly like you would hope. The one little sticky wicket is you do have to recognize that you might get a different answer in a different direction. And so, for example, if we're looking at x partials, right, the x cross-section could go the other way. So, for example, for this function here, we have two different second partials. One's plus, one's minus. because in one direction, like in the sort of the, I don't know, sort of the peak to peak of the Pringle, right? This is concave up, but sort of going over the pass, as it were, of the Pringle is concave down. There is no single variable version of this. This is a brand new phenomenon that only happens in multivariable calculus. So anyway, good place to draw the line. We will pick up here on Friday. Y'all have a good rest of your week.